Hi, I'm Mark Doley, and today I'm going to present working energy. Earlier I showed how working energy was related to Newton's second law, and now I'm going to give 3 examples of different ways to relate it to Newton's second law. And the first way that I'm going to do it is by solving for F equals ma, and then using rectilinear motion to solve for distance. And so our problem is given, we have 2 blocks on an inclined plane, and they're attached by a string going over a pulley, frictionless and massless. And we're given the weight of block A equals the weight of block B equals 50 pounds. And the coefficient of kinetic friction is 0.05, and the blocks are initially at rest. So once we let them go, they're going to start moving. And we're trying to find the velocity of each block after they move 1 foot. And the method that we're going to use is Newton's second law, F equals ma, and also rectilinear motion. And our unknowns, sometimes you can think about these before you start the problem, sometimes you don't get to them after the problem. Usually when I'm done doing a problem, I like to organize it all out. I go back and redo the problem and see, and only put the essentials down so that I can look at it later and see what happened. So for this problem, I know that the unknowns are tension, the acceleration of block A, and the acceleration of block B. And the relationships that I'm going to use to solve for the 3 unknowns, that means I'm going to need 3 relationships. What are those going to be? Well, we can always get a relationship from block A, we can always get a relationship from block B, and when we have a cable, we can get a cable relationship. And our cable relationship tells us that however much block A moves, block B is going to move the same amount because the cable doesn't stretch. And so I make a free body diagram for block A, and to do the free body diagram, I like to first, I don't draw the box because all the lines get in the way. I just like to draw the inclined plane and designate one of the directions positive x. I chose this positive x. It's inclined at 45 degrees. That means I drop the weight straight down, and the weight is coming down on the x-axis 45 degrees from the y-axis, and this angle is going to be the same as this angle every time. And our normal force is coming up normal to the x-axis. And we have the sum of our forces equals the mass of block A times the acceleration of block A. And I've also designated the direction of the acceleration. I say, actually, this is going to be, I think that it's going to be moving in the negative x direction. And I think that because this is at a higher angle over here, so I think it's going to fall down that way. If I'm wrong, in the end, all it's going to do is it's going to give me a negative answer for acceleration, so it doesn't really matter. But I try to choose the correct direction. And so sum of my forces, so I have the weight in the x direction, or it's going to be negative, plus tension in the x direction, it's going to be positive, plus friction in the x direction. I didn't draw my friction in. And so my friction is going to be this way because I think my block's going to be moving that way. And so that's going to equal mass of block A times the acceleration of block A. Negative. Negative because I have the way that I've drawn my arrow here, it's in the negative x direction. So the equation, once I substitute all these numbers, all of these numbers here, the friction, the mass of block A, and the force due to the weight of gravity in the x direction. All these can be determined using Newton's second law, and that's something that is done previously. I don't have enough room to go through and do all that, but those calculations are fairly simple. And so I substitute in, simplify the equation, and I get my tension equals 33.59 minus 1.55 times the acceleration of block A. So I have two variables. I'll leave it at that. And now I'm going to have to switch over to another blackboard, and we can see